Welcome back. Today we're going to be going over the universal law of gravitation. We have talked about the force of gravity a lot in this class, but now we're going to talk about why it exists and how to solve for it. And the idea about the force of gravity is that the force of gravity is really an attraction between any two objects with mass. So if you have mass and a person next to you has mass, then there is an attraction between you. Your masses pull against each other like two magnets. So here's an object, mass 1, here is an object, mass 2, and these two objects pull on each other with forces of gravity. And the size of those forces are equal in size and opposite in direction. That's the nice thing about physics, is you can't be more attracted to somebody than they are back to you. That's Newton's third law, says that they are equal in size and opposite in direction. And it's this invisible force pulling you two together, this invisible attraction that we call the force of gravity. Every two objects with mass pull on each other with some amount of force. And so the equation to solve for how much force do the two objects pull on each other with, it depends on the mass of object 1 in kilograms. It depends on the mass of object 2 in kilograms. But it also relies on the distance between those two masses. And so when we deal with the distance between those two masses, sometimes that distance is labeled as an R. R stands for how far apart those distances are, and that R value is squared. So when we're dealing with the force of gravity, you have mass, the other person has mass, and the distance that you guys apart are needs to be squared. So M stands for the mass of the object measured in kilograms. R stands for the distance between the two objects measured in meters. And so it would be a really large number that you would have as a gravitational attraction between any two objects if there wasn't just one other factor. And this other factor that happens is just a capital G. Capital G is a constant. Capital G is the same number all the time. It's 6.67 times 10 to the negative 11. This is provided for you on the equation sheet. You don't have to memorize it, but sometimes it's nice to store it in your calculator so you don't have to type it in all the time, especially since we're doing times 10 to the negative 11th, which we would use that capital E button on your calculator in order to plug it in. So the idea here is that there's an attraction between all two objects with mass. And so what we would do is we would say, all right, well, how much mass does one person have? How much mass does the other person have? And let's measure the distance between them. When we measure the distance between them, we're not going to do hand to hand or foot to foot. Instead, what we really want to do is center of mass to center of mass. And if you want to be cute about it, you could call it heart to heart. Really, the distance between the two objects is the distance between their two centers of mass. And so we could say that, one person has an object of 50 kilograms and the other person has an object of 65 kilograms. And maybe that we are going to be 2 meters apart from each other. Let's solve for that force of gravity acting on us. So we would say, okay, the force of gravity is going to be equal to G, which is 6.67 times 10 to the negative 11, times the mass of object 1, which is 50, times the mass of object 2, which is 65, and then all divided by the distance between the two objects. Don't forget to square it. So when you plug all of that into your calculator, you would be able to find the force between the two objects is not a very large force at all. That really we are not very attracted to each other due to a force of gravity, that those forces are rather weak when we're talking about just people. In order to have a strong pull of gravity between two objects, you want to have a larger mass. The more mass the object has, the more you're attracted to it. You'll notice that we don't draw force diagrams that have attractions between people because these number values are really weak. What I'm going to type into my calculator right now is 6 second, and then it's right above the number 7. It's a capital E button. So 6.67 second E negative 11 times 50 times 65 and divide that whole thing by 4. And so I am going to get a really small number. That force of gravity between the two people is 5.4 times 10 to the negative 8th newtons. In order to be more attracted to something, really what we'd want to do is say, okay, let's talk about the attraction between a person and the earth. Because the earth has a large mass, and so then we'd be able to say, oh, I'm actually rather attracted to the earth because it has such a big mass. And so when we're trying to figure out what the mass of the earth is, we're allowed to just go ahead and Google it and say mass of earth in kilograms. So 5.97 times 10 to the 24th, 5.97 times 10 to the 24th kilograms. That's the mass of the earth. And now let's take a person who's 50 kilograms and put them on earth. The mass of the person is going to be 50 kilograms. But what would we use as the distance between the two objects? Would we say it's 0 because the person's standing on the earth? No. Instead, we would have to say, okay, we're measuring that distance from heart to heart. What that really means is from the center of the earth to the center of the person. Heart to heart. And so from the center of the earth up to the person, that value is actually the radius of the earth, which again, we can look up what the radius of the earth is in meters. And see 6.37 million meters. So 6.37 times 10 to the 6th meters. That's what the radius of the earth is. So we could add plus the distance to your center of mass, but that's like a half a meter, maybe 1 meter. And 1 meter is really not significant when we're talking about 6 million meters. So really, when we're trying to find the attraction between people and the earth, we would just use the radius of the earth as the distance between the two objects. So now when we're using that same equation, that Fg equals gm1 m2 all over r squared, we'd be able to solve for our attraction between ourselves and the earth. So 6.67 times 10 to the negative 11 times our mass, 50 kilograms, times the mass of the earth, 5.97 times 10 to the 24th. That whole thing divided by the radius of the earth, 6.37 times 10 to the 6th squared. Plugging this into your calculator is hard, and I recommend doing it with me right now. 6.67 second E, that capital E should be showing up on your screen, negative 11 times 50 times 5.97 second E 24, and then I hit enter and I find out what that answer is, and then I do divided by parenthesis 6.37 second E 6 parentheses squared. And so what I'm going to get here as my answer is I'm going to get 490.7 newtons. That is the force of gravity between me and the earth. But wait a minute. Don't I already have a way of finding a force of gravity between me and the earth? Isn't it just my mass times G, the gravitational field strength of the earth? What would 50 times 9.8 be? 490 newtons. Turns out that in order to solve for the force of gravity between two objects, you need to know the mass of the two objects and the distance between them, and that G value. Or that if you're on Earth, you can somehow figure out the force of attraction between you and the Earth by taking your mass times lowercase g. I guess that means that this equation, force of gravity, equals G m1 m2 all over r squared, is the same thing as the force of gravity equals m times g. I think that means that this right here is the same as this right here. That G for the planet Earth could be solved for by doing G times the mass of the Earth divided by the radius of the Earth squared. All right, that was your introduction for solving for the force of gravity between two objects. But what I want to do along with the math is just a quick review of what these relationships are. As we look at this equation right here, we can see that mass is going to be directly related to the force of gravity. What that means to be directly related to the force of gravity is that as the mass goes up, the force of gravity goes up. So increasing the mass increases the force of gravity between two objects. So that's a direct relationship. But the distance between those two objects is an inverse relationship. In fact, it's not just an inverse relationship. That distance is related to the force of gravity in an inverse squared relationship. So this distance is inversely related to the force of gravity, but it's inversely squared related to the force of gravity. As your distance goes up, your force of gravity goes down. And so we'll do some proportional reasoning with this equation. We'll say that for that equation of the force of gravity equals G m over r squared, that to do proportional reasoning means to put boxes on. These boxes are for factors of change. When we're talking about factors of change, we put a box in front of each variable. And really, when we're putting these boxes in front of each variables, we'll say that, all right, whatever you do to the mass, you're going to do the same thing to the force of gravity. Whatever you do to this mass, you're going to do the same thing to the force of gravity. You can't ever change G. G is always going to have a 1 in its box. It's not even worth writing. G is a constant. It can't change. But whatever happens to the distance, we're going to divide by that value. But notice how the distance is squared, which means that you have to square your factor of change. And so what that tells you is that doubling the distance is going to decrease the force of gravity, but doubling the distance does not cut the force of gravity in half. If we keep all other things the same, we'll see that when we're twice as far apart, double the distance, that the attraction between us, or our force of gravity, is going to be cut into 1/4. It'll be 1/4 as strong. That's what it means to be an inverse squared relationship.